ourselves of the difference quotient. So if you think back to the last algebra class you took, you may have talked about this expression called the difference quotient. So if I have some function f of x, the difference quotient is f of x plus h minus f of x over h. So if I am given the function f of x equals x squared plus 2, and I want to find and simplify the difference quotient, then I need to find f of x plus h, which remember is just my function with x plus h plugged in. So in this case, I'd have to plug in an x plus h everywhere I see an x in my function. So we would have x plus h squared plus 2. So that's the f of x plus h part of the difference quotient. And then we subtract f of x, so we're subtracting the entire function. So we have minus x squared plus 2. And then this is all over h. So this would be the unsimplified difference quotient. So if we want to simplify this, we have this x plus h squared, so we're going to have to FOIL that out, which would give us an x squared plus an xh plus an xh, so plus 2xh plus h squared. Then we have the plus 2. And if we distribute this negative sign, we have minus x squared minus 2 all over h. And now you see that we have some like terms that we can combine. We have a positive x squared and a negative x squared. We have a plus 2 and a minus 2. So we are left with a 2xh plus h squared over h. And we can factor an h out of the numerator. And so we have h times 2x plus h over h. And now we cancel that common factor, and we're just left with 2x plus h. So this is the simplified difference quotient. Now you may recall that the average rate of change of a function between 2 points is just the slope of the line that would connect those 2 points. So on the graph here, you see we have the point A, f of A, and we have the point B, f of B. And so remember, to find slope, slope was just equal to y2 minus y1 over x2 minus x1, right? Or the change in y over the change in x. So if I want to find the slope of the line connecting these 2 points, I can take my y2 minus my y1, or f of b minus f of a, so that's the change in y, over my change in x, or my b minus a. And so this line connecting these 2 points, we're going to call this the secant line. So the average rate of change between 2 points is just the slope of the secant line connecting those 2 points. So if we look at an example, suppose that the total profit in hundreds of dollars from selling X items is given by the function p of x equals 2x squared minus 5x plus 6. We want to find the average rate of change of profit from x equals 2 to x equals 4. So to find the average rate of change, we're going to want to evaluate p of 4 and we're going to evaluate p of 2, subtract those two values to get the change in y, and then we'll divide by the change in x, which is 4 minus 2. So if I plug 4 into p of x, I am getting 18. And if I plug 2 into this function, I'll have 2 times 2 squared minus 5 times 2 plus 6, which is 4. So we get 18 minus 4 in the numerator over 4 minus 2, which gives us 14 over 2, or 7, and profit is in hundreds of dollars from selling X items, so our average rate of change in profit would be $700 per item. And so this is a little applet in GeoGebra, and if you're looking at the PowerPoint slides that are posted in Blackboard, there's a link for you to click on so that you can play around with this yourself if you want to. And so you can see that they have a function graphed here. And instead of labeling these points A and B, they've labeled the first point as C on the x-axis, and you can see that I can slide this point around. And the second point they're calling C plus H. Right? We're starting at C and then adding a little bit on the x-axis, so it's C plus H. And so let's see. There's a box I can click here that says Show Secant Line, and if I click on that, now it's showing me the line connecting C and C plus H. Now, if you see this dotted line in purple that's just sort of touching my graph at C, this is the tangent line to my graph at C. And it would be a little tough to find the slope of this line because I know only one point. I know that the point C, f of C, lies on this graph, but I don't have any other points. So what I can do though is if I look at my points C and C plus H, if I just let H get smaller and smaller and smaller, you can see that the secant line starts to get really, really close to that tangent line. So if I start by taking the slope of the secant line, and then I take the limit as H shrinks down to 0, then I can find the slope of that tangent line at C. And so if you look at this slide, here again, now on this slide we're using A instead of C, but if I label this as the point A, f of A, and this is the point A plus H, f of A plus H, then to find the slope of that secant line, I would have my f of A plus H minus f of A over A plus H minus A. And so we can simplify that denominator a little bit. We have f of A plus H minus f of A over H. And so this gives us the slope of that secant line. But as we let H get smaller and smaller and smaller, then the secant line starts to approach that tangent line. And the slope of this tangent line gives us what we're going to call the instantaneous rate of change at A. So to find the instantaneous rate of change at a point, we're going to take the limit as H approaches 0 of f of A plus H minus f of A over H, provided, of course, that the limit exists. So if I'm given a function, f of x equals 2x squared plus 3, and I want to find the instantaneous rate of change at x equals 1, well, remember the formula for the instantaneous rate of change at some point A. It's the limit as h approaches 0 of f of a plus h minus f of a over h. So this would be the limit as h approaches 0. And in our case, we want the instantaneous rate of change at 1. So we want f of 1 plus h minus f of 1 over h, which would be the limit as h approaches 0. Now to find f of 1 plus h, remember we just plug a 1 plus h in everywhere we see an x in our function. So we would have 2 times 1 plus h squared plus 3. And then we want to subtract the function with 1 plugged in. And so if I plug 1 into this function, I'm going to get 2 times 1 plus 3, so 5. So minus the f of 1 all over h. And we can simplify a little bit more. We have the limit as h approaches 0 of 2 times, now we have 1 plus h squared. So when we FOIL this, we'll get 1 plus h, so plus 2h, plus h squared. And then we have plus 3 minus 5 over h. And I can distribute that 2 to get the limit as h approaches 0 of 2 plus 4h plus 2h squared plus 3 minus 5 over h. And if we combine like terms, we have a 2 plus 3 minus 5, which is 0. So this is the limit as h approaches 0 of 4h plus 2h squared over h. And I can factor an h out of that numerator. So we have the limit as h approaches 0 of h times 4 plus 2h over h. And I'll cancel that common factor. And I'm left with the limit as h approaches 0 of 4 plus 2h. And as h goes to 0, this will just be 4. Now, a quick definition. When we talk about marginal cost in this class, marginal cost can be thought of as the instantaneous rate of change of the cost function at a particular point. It's the cost of producing one additional item. So when you see a question and it asks you about marginal cost at a point, you're thinking about the instantaneous rate of change of that cost function at your point. And the same kind of thing holds if we're talking about marginal profit or marginal revenue. So if you look at this question, it says, suppose that the total profit in hundreds of dollars from selling X items is given by P of X equals 4x squared minus 6x plus 10. We want to find and interpret the marginal profit when X is equal to 2. So really, we're just looking for the instantaneous rate of change of this function at 2. So we need to find the limit as h approaches 0 of p of 2 plus h minus p of 2 over h. So this will be the limit as h approaches 0 of 4 times 2 plus h squared minus 6 times 2 plus h plus 10. So all of that is the P of 2 plus H minus P of 2. So if I plug 2 into my function, I am getting 14 all over H, which is the limit as H approaches 0 of 4 times. Now if we FOIL the 2 plus H squared, we'll get 4 plus 4H plus H squared minus 6 times 2 plus H plus 10 minus 14 all over H. And now we can distribute to get the limit as H approaches 0 of 16 plus 16H plus 4H squared. And if we distribute the negative 6, we'll have minus 12 minus 6H plus 10 minus 14 all over H. And I'm going to move to the other side of the screen to have a little more room. This can simplify to the limit as H approaches 0. So we've got 16 minus 12 plus 10 minus 14. So 16 minus 12 gives us 4, plus 10 gives us 14, minus 14 is 0. So we have the limit as H approaches 0 of 16H plus 4H squared minus 6H over H. And I can factor an H out of the numerator. So that would be H times 16 plus 4H minus 6 over H. Cancel the common factor. And we have the limit as H approaches 0 of 16 plus 4H minus 6, which is just 16 minus 6, or 10, as H goes to 0. So recall that total profit was in hundreds of dollars for selling X items. So this means that when X is equal to 2, the profit to be made from selling one more item would be $1,000.